Hello students, welcome to EPG Pathshala. I am Dr. Nidhi Handa from Gurukul Kangri Vishwavidyalaya Haridwar. Today we are going to talk on module continuous distribution, normal distribution, normal curve under the paper quantitative techniques for management decisions. After completing this module, you should be able to understand the introduction, continuous probability distribution, then what is normal distribution, normal probability distribution, then tables are also discussed for the normal distribution, and in the end, summary. Continuous probability distribution. We define a continuous random variable as a random variable whose values are not countable. A continuous random variable can assume any value over an interval or intervals. Because the number of values contained in any interval is infinite, the possible number of values that a continuous random variable can assume is also infinite. Moreover, we cannot count these values. The life of a battery, we cannot count. Height of persons, this is a continuing process. Time takes to complete an examination, this is also considered to be continuing process. Amount of milk in a gallon, weights of babies, prices of houses, all are example of continuous random variables. Note that although money can be counted, usually at variable involving money are considered to be continuous random variables. This is so because a variable involving money often has a very large number of outcomes. Suppose there are 5,000 female students enrolled at a university, and X is continuous random variable that represents heights of these female students. Table 1 lists the frequency and relative frequency distribution of X. As you can see, frequency and relative frequency distribution of heights of female students. Heights of a female student in inches are given, then frequencies are given, then it's relative frequency, as you know, each frequency divided by 5,000. Then we get relative frequency, and sum of all the relative frequencies will be 1. The relative frequencies listed in above table can be used as an approximate probabilities of respective classes. We take first figure, histogram and polygon for table 1. If we see in the table, first entry is 60 to less than 61. These are all heights of a female student in inches. So corresponding to it, the frequency is 90, and less than 60 we will plot in the figure like 60 to 61. In the middle, we make histogram, and then next entry is 61 to 62. So again, mid value of 61 and 62, because the entry according to table 61 to less than 62. From 61 to 62, second entry. From 62 to 63 is third entry. So we will take midpoint of 2 points. So 62 and 63, midpoint will be 62.5, which is more than 62 and less than 63. So again we will take midpoint of 62 and 63, and corresponding to it we will plot frequency. Frequency is 460. So 460 is taken, and accordingly relative frequency to 460 is 0.092. So we will plot here 0.092. 0.092 is a number which is less than 1, and so on. So this figure we will plot all the values, and we will see that this will match to bell-shaped curve. Not exactly bell-shaped curve, but it is likely to be. Similarly, in the second figure, which depicts the probability distribution curve for heights, we will take a flow of polygon, we draw a curve, and of course both figures are similar. Here also midpoints are plotted, and on x-axis 60 to 61, 61 to 62, and 62 to 63, so on, values are taken. And if we see that the highest frequency, then we note that highest frequency is 970 and its relative frequency is 0.194. So corresponding to highest frequency, we see the class interval that is 64 to less than 65, between 64 and 65. So between 64 and 65 histogram is the highest, because here the highest frequency corresponding to it. This make unimodal or peak of the curve lie in the interval 64 to 65. Figure 1 displays the histogram and polygon for the relative frequency distribution of table 1. Figure 2 shows the smooth polygon for the data of table 1. The smooth polygon is an approximation of probability distribution curve of the continuous random variable x. Note that each class in table 1 has width equal to 1 inch. If the width of classes is more than 1 unit, we first obtain the relative frequency densities, then graph these relative frequency densities to obtain the distribution curve. You can see carefully the both two figures given. The relative frequency density of a class is obtained by dividing the relative frequency of that class by the class width. The relative frequency densities are calculated to make the sum of the area of all rectangles in the histogram equal to 1. The probability distribution curve of a continuous random variable is also called its probability density function. The probability distribution of a continuous random variable possesses the following two characteristics. The probability that x assumes a value in any interval lies in the range 0 to 1. The total probability of all the intervals within which x assume a value is 1.0. So total probability or total area under the curve is 1.0. The first characteristic state that the area under probability distribution curve of a continuous random variable between any 2 points is between 0 and 1, as shown in figure. The second characteristic indicates the total area under the probability distribution curve of a continuous random variable is always 1 or 100%, as shown in the figure. Shaded, you can see in the figure. In figure 4, total area under a probability distribution curve, which is shown, is 100%. The probability that a continuous random variable x assumes a value within a certain interval is given by the area under the curve between two limits of the interval, as shown in figure 5. The shaded area under the curve from A to B in this figure gives the probability that x falls in the interval A to B. That is, probability A is less than equal to x less than equal to B is equal area under the curve from A to B. Note that interval A less than equal to x and less than equal to B states that x is greater than or equal to A but less than or equal to B. Reconsidering the example of heights of all female students at a university. Now in figure 5, area under the curve as probability. Shaded area gives the probability between 65 to 68. This area is according to table more than 65 and less than 68. So this area is between 65 and 68. Now we see if the consider figure 7. Here probability of a single value of x is 0. As we see the histogram for 67, 67 comes in the interval 65 to 67. If we see the table, 60 because 66 to less than 67 corresponding to this class interval frequency is 640, and then 67 to less than 68 corresponding to it the frequency is 440. Now if we see the at point 67, x is equal 67, then we will say that this area, that the single value of x is 0. We will show it like this: probability of x is equal to 67, which is 0. The probability that height of a randomly selected female student from this university lies in the interval 65 to 68 is given by the area under the distribution curve of heights of all female students from x is equal 65 to x is equal 68 as shown in figure 6. The probability is written as probability P such that 65 is less than equal to x less than equal to 68, which states that x greater than or equal to 65 but less than or equal to 68 for a continuous probability distribution. The probability is always calculated for an interval, remember. For example, in figure 6, the interval representing the shaded area is from 65 to 68. Consequently, the shaded area in that figure gives the probability for that interval. The probability that a continuous random variable x assumes a single value is always 0. This is so because the area of a line which represents a single point is 0. For example, if x is the height of a randomly selected female student from that university, then the probability that this student is exactly 67 inches tall is 0. That is, probability x takes value 67 is equal 0. This you will see in the figure on the x-axis. This probability is shown in figure 7. Similarly, the probability for x to assume any other single value is 0. In general, a and b are two values that x can assume, then probability of a is equal 0 and probability of b is equal 0. From this, we can deduce that for a continuous random variable, probability of a less than x less than b is equal probability of a less than equal to x less than equal to b. In other words, the probability that x assumes a value in the interval a to b is same whether or not the values a and b are included in the interval. For example, on the heights of female students, the probability that a randomly selected female student in between 65 and 68 inches tall is same as the probability that this female is 65 to 68 inches tall. This is shown in the figure. Note that the interval between 65 and 68 represents 65 less than x less than 68, and it does not include 65 and 68. On the other hand, the interval from 65 to 68 represents 65 is less than equal to x and less than equal to 68, and it does include 65 and 68. However, as mentioned previously, in the case of a continuous random variable, both of these intervals contain the same probability or each under the curve. The normal distribution is one of many probability distributions that a continuous random variable can possess. The normal distribution is the most important and most widely used of all the probability distributions. A large number of phenomena in the real world are normally distributed either exactly or approximately. The continuous random variable representing the heights, weights of people, scores on examination, weights of packages, for example, cereal boxes, boxes of cookies, etc., amount of milk in a gallon, life of an item such as a light bulb or a television set, and the time taken to complete a certain job have all been observed to have approximate normal distribution. The normal probability distribution or the normal curve is given by a bell-shaped symmetric curve. Such a curve is shown in figure 9. It has a mean of mu and a standard deviation of sigma. A continuous random variable x that has a normal distribution is called a normal random variable. Note that not all bell-shaped curves represent a normal distribution curve. Only a specific kind of bell-shaped curve represents a normal curve. So normal probability distribution is, if we notice, when plotted, gives a bell-shaped curve such that total area under the curve is 1.0. The curve is symmetric about the mean. The two tails of the curve extend indefinitely. A normal distribution curve possesses the following three characteristics. One is the total area under a normal distribution curve is 1 or 100%. Now, if we consider figure 10, total area under a normal curve. As you see that it is extended indefinitely because the curve does not touch the grounds, that is x-axis, on the left hand side as well as on the right hand side. So this can be extended indefinitely to the left hand side and to the right hand side. Second is a normal distribution curve is symmetric about the mean as shown in the figure 6. Consequently, half of the total area under a normal distribution curve lies on the left side of the mean and half of the total area lies on the right hand side of the mean. 50% of the area, if we see figure 11, normal curve is symmetric about the mean. Mean where mu lies, here this is a separating line coordinating to mu. So towards left hand side 50% of the area and towards right hand side 50% of the area. Again, the curve is not touching the grounds, that is x-axis. The tails of a normal distribution curve extend indefinitely in both directions without touching or crossing the horizontal axis. Although a normal distribution curve never meets the horizontal axis beyond the points represented by mu minus 3 sigma and mu plus 3 sigma, it becomes so close to the axis that the area under the curve beyond these points in both directions can take as virtually zero. Next, in figure, we will see that standard deviation are different. One curve and mu is 50 for all the three curves. When mu is equal to 50 and standard deviation is 5, then this is peaked curve, this is on the highest. When the sigma is 10, then it is the second lower or in between curve, and when sigma is 16, this curve is normal curve. For this, mu is equal 50. So in between the curve is also known as mesokurtic curve. Platokurtic and leptokurtic, three types of curves there. The mean mu and the standard deviation sigma are the parameters of the normal distribution. Given the value of these two parameters, we can find the area under a normal distribution curve for any interval. Remember that there is not just one distribution curve, but rather a family of normal distribution curves. Each different set of value of mu and sigma gives a different normal distribution. Notice it. The value of mu determines the center of a normal distribution on the horizontal axis, and the value of sigma, notice students, the value of sigma gives the spread of the normal distribution curve. The three normal distribution curves drawn in figure 13 have the same mean. You can see in the figure very carefully. The three normal distribution curves drawn in figure 13 have the same mean but different standard deviations. By contrast, the three normal distribution curves in figure 14 have different means but the same standard deviation. Now in figure 14, we see that different mu's are taken, different mean values are taken, and sigma is same for all the three curves. So height of the curve is same, which is same in all the three curves. Mu is 20, then sigma is 5, mu is 30, and sigma is 5, mu is 40, and sigma is 5, three different curves and with the same standard deviation. Like the binomial and Poisson probability distribution, the normal probability distribution can also be expressed by a mathematical equation. However, we will not use this equation to find the area under a normal distribution curve. Instead, we will use tabular values. You can also consult. Now in figure 14, we see that different mu's are taken, different mean values are taken, and sigma is same for all the three curves. So height of the curve is same, which is same in all the three curves. Mu is 20, then sigma is 5, mu is 30, and sigma is 5, mu is 40, and sigma is 5, three different curves and with the same standard deviation. Different tables are given. Here we take this standard normal table. The entries in the table gives the area under the standard normal curve. If we see the table in tabular values, table is Z takes value, we will see vertically downward, then it takes 0, 0.0, 0, 0.1, 0, 0.2, 0, 0.3, 0, 0.4, so on, 1.0, then 1.1 and up to 3.0. The last entries for Z values are 3.0, and horizontal wise we see that Z takes value 0.00, 0.01, 0.02 and like this 0.09. So this values be taken as, for example, the value 0.0478 corresponding to this Z value will be 0.12. 0.12, if Z is equal to 0.12, then corresponding area will be 0.0478. Like this you will see the different entries and you will see the curve. Only 3.0 or 3.9 we have taken for Z value, the last, and rest of the area which cover under x minus 3 mu or x plus 3 mu, that covers area which we have considered x minus mu minus 3 sigma and mu plus 3 sigma, that covers under 3.09. Rest of the area we will subtract from 0.5 and we will get the area. So in questions further we will take these examples, then you will understand the meaning of it when you take up questions. This explanation will be more clear to you in the next module. So students, let us now summarize what we have learned in this module. A continuous random variable can possess one of many probability distributions. In this module, we have discussed normal probability distribution. This distribution is also an approximation to the binomial distribution. The possible values that random variable can assume are infinite and uncountable. Continuous random variable can be defined as a variable that can assume any value in one or more intervals. Characteristics play an important role for the probability distribution of a continuous random variable. Characteristics of normal probability distribution are also discussed. The mean and standard deviation are parameters of normal distribution. Different values of standard deviation have been also discussed here. Thank you.